So today we're gonna, so today I will give a quick introduction to the PI talk theory, and then the next lecture will be talking about sort of integral version of the so-called Fontaine-Laplace theory. So this is the aim of these lectures are not for you to sort of understand PI talk theory right away, but somehow the purpose is somehow for you to, I guess, see a little bit what it looks like, and then. But we're going to only use a very tiny bit portion of it. So, okay. So let's sort of talk about where the question of PI talk theory comes from. So to start, let's take X be a proper and smooth variety of dimension D over a field K. Let's first of all talk about so-called Durand cohomology. So from this, I get the relative differential sheaves. This is locally free because smooth is locally free over graph D. And then once I have this, I can set omega x over ki for any I to be the exterior power of this locally free sheaf. So this sheaf will be also locally free of rank D true psi, so rank D true psi. And then I can form the Durand complex. Which is omega x dot. It's a complex of sheaves. OX, the differential goes to the first, I guess, the sheaf of differentials. Note that this is not a homomorphism. This is not a homomorphism of coherent sheaves. This is just, this is just a morphism of sheaves. Doesn't respect the OX linear structure. Same here. We can continue on. A key property is that if you do something twice, you get 0. So this is something I can probably learn in calculus. So I can define the so-called algebraic Durand cohomology. To be the hypercohomology of this complex. We denote that by H Durand star X over K, which is the hypercohomology of this complex. Okay. So, because of definition, let me write down a calculation to calculate this hypercohomology. So we have a spectral sequence. So how do I write that spectral sequence? It's in the sort of the first quadrant. So I write H0 of x omega x, excuse me, OX. And then the idea is that we want to first of all take cohomology of each of the terms in the complex, and then take the differential in the complex. The cohomology of each of the terms, that cohomology is taken sort of vertically upwards. So I have H1 x OX, and H2 x. And then I take this direction. So this is actually my E1 thing. Right. So H0 of x omega 1 x H0 of x omega x2 so on and so forth. And again vertically I'm taking the the usual check homology. So I'm going to write all of it. Okay, just like so. And this will converge to H Durand. Algebraic Durand cohomology of X over K. So this here's a fact. Not a very easy fact. When characteristic of K is 0, this spectral sequence degenerates at E1. Namely, all these maps, after you take the check component already, these maps are already 0. In characteristic 0. Oh, I should put these over K here. I'm going to sort of list these things later on. Okay. So therefore, all these maps are 0. So I mean, we're going to be later only mostly consider this check characteristic K equals 0 case. So all these maps are 0. So in this case, when these are mapped 0, and also so on the next page are all 0. So this is sort of the last page when we can figure out what this Durand coupling is. Then, therefore, let's take an example. Let's say what do we know about the second cohomology of the Durand cohomology? The second Durand cohomology. The second cohomology, well, if I want to look at the second cohomology, I want to look at sort of the entries where the x and y indices adds up to 2. So they like these 3 pieces. Okay? So this the second Durand cohomology will be composed of these 3 things. But there's an additional structure in any sort of spectral sequence as so. The additional structure is that somehow there's a filtration on it. The sub-object is this one. So the filtration goes like this. So this H0 x omega 2 is a sub-object in this H2. And then there's a sort of secondary sub-object. Namely, quotienting out this part, this becomes a sub-object. And this is a quotient of this H2. So I like to write things in terms of so-called extensions. So I'm going to write this. Dash means an extension, which I don't specify in the class. Sometimes it's not so easy to write down what the class is. H2 of x O x. Okay. So let's see. So this is a canonical sub-object. And this is a canonical quotient object. Okay. Or put another way, or equivalent, or another way. I have a filtration on this second Durand cohomology, such that it's a decreasing filtration. So let me maybe say when I smaller than 0, because it's decreasing. This is I smaller than or equal to 0. This is the whole thing. And I being 1, this is so I being 1. So if I listen to 0, this is the whole thing. When I being 1, you only have this sort of the first 2 parts. So then like try to write it short. Extension is 1. X omega x over 1. And I 2, you just have the first term, the sub-object. And I bigger than 2, you get 0. So that's what roughly what the Hodge filtration looks like. So in general, so we have a decreasing filtration. In fact, we can write down what these things are. And the end result will be just sort of you just see these things. In the sense that, for example, I equals 1, you only see omega 1 and omega 2 terms here. And this OX term doesn't show up. Okay. So that's all I want to say about the Durand cohomology. Now let's talk about how this Durand cohomology compares with other cohomologies we know. So we'll put ourselves in a very careful situation. I want to not just only work only sort of everybody close to it. I want to work with sort of not close to it. So let's start with the reals. So i.e. my X is a proper smooth variety over reals. In this case, we have an isomorphism. The following. So, although it happens over reals, but the comparison, I have to talk about sort of the complex point of this X. I mean, basically just write the defining equation for X, which is in R, and then solve it in C. So take the corresponding, I guess, complex manifold associated to such, or not, a complex manifold associated to such a proper smooth variety over R, and I take the Betti cohomology, or the singular cohomology, in Q coefficients. I can tensor that with C. It's a classical Hopf theory. It says that this is isomorphic to the Durand cohomology. Durand cohomology. But then I have to remark that I want to be very, very careful here when we talk about these cases. Namely, the Betti cohomology really have coefficients in Q. What we're doing is that we're base changing that coefficient to C. On the other hand, Durand cohomology has, because the variety is defined over R, so the Durand has intrinsically defined over R. And then I base change to C. And then the classical Hopf theory says that these two are isomorphic. Namely, the single Betti cohomology or singular cohomology with C coefficients is isomorphic to the Durand cohomology with C coefficients. Because, so this is a Durand comparison over C. So I want to add one more thing. Because that my variety X is defined over R, I'm comparing it, I'm sort of basing everything into C. So there's additional structure here. Namely, if we let the Galois group of C over R, which is sort of two elements, 1 and C, C being the complex conjugation, the C will act over here. Because C will act on the C point of this X by, just write down the coordinate, change the sign on the imaginary part. And C will act on this coefficients here. C doesn't act on here. Because this is purely over R, C will fix everything. But then complex conjugation will act here. And I want to say that for the diagonal action of C on these two terms, that's under this isomorphism that's going to be equivariant for the C action on the coefficient over there. So this is an equivariant. The Galois group of C over R equivariant. So we have a little bit more than just an isomorphism of C vector spaces. We also know that somehow this isomorphism is compatible with the Galois equivariance. Or put it another way, suppose that I want to know what this term is. What we can do is that we can take the Betti cohomology and tensor that with C and let the complex conjugation to act diagonally on this. And by this isomorphism, I'm going to get the right-hand side. But then after I take the C invariance, then if I take C invariance, this will kill the C term. I'm going to left with the right. So this is something I'm going to, sort of in PI talk today, we're going to explore later on. Of course, we are not going to explore the C and R. R and C. So now I want to take my K to be complete discrete value in the field of characteristic 0. That's the residual field. We call it small k is is Grothendieck's idea. And I'll later explain the work of Fontaine, which somehow kind of completed this prediction of Grothendieck. Grothendieck was like, okay, he looked at this R and C picture, and he wanted to know what's happening when we're working with this K for a power sequence variety over K. So on the left-hand side, one has to replace the singular beta cohomology by the so-called étale cohomology. We're not going to sort of spend too much time on explaining what the formula of étale cohomology, which is somehow pretend that this is roughly the same thing as singular cohomology. In fact, it is roughly the same thing as étale cohomology, somehow in terms of dimension and all that. Except it has additional information. We'll say that in a minute. So then, I'm over a p-adic field. But then my étale cohomology, even I'm over a p-adic field, but this K has still captures to 0. I can take the étale cohomology with coefficient QP. So the only comparison, well, roughly speaking, this is if you fix some sort of if you fix an isomorphism between A bar and C, then you can take sort of C points of this, take an identification of this, and then take QP. So these are isomorphic. There's a canonical isomorphism. Depending on what this isomorphism is, this identification of C with K bar is. But this isomorphism lost some information, namely, whenever you have étale cohomology of this naturally carries an action of the Galois group. So that's additional information you get by working with so-called étale cohomology. Except that you can just somehow pretend it's just a singular cohomology. So that's why when people talk about how I think of étale cohomology, I don't think about the axioms. I think that's just a singular cohomology. There's nothing different here. Okay, so now on the other side, I still have the Durand cohomology, which is x over k. Okay, so if somehow the goal is somehow have a similar structure as above, namely I have what am I saying? The étale cohomology should be comparable to the Durand cohomology. But then they don't compare on the ground field. In fact, they don't have the same ground field. I mean, over here you have somehow QP here. Over here you have the K here. I deliberately didn't write K equals QP, because, although our later application will be K equals QP. But I deliberately write this K because these are intrinsically different things. This is a coefficient, this is the ground field of the proper sequence variety, X. So now I have to tensor with something. So Grothendieck's question was that what should be put in this question mark so that you have a comparison. So this was answered by Fontaine. He constructed a ring called B Durand. We'll review its definition later. So Fontaine constructed the ring. It's not no longer a field as the C here. This is some sort of a crazy ring, a little bit crazy ring, B Durand. This B Durand ring carries an action of the Galois group of K. And also, this also has a filtration. Let me put a filtration here. Although it's not an action, but we're just going to say there's a filtration here. Similarly here, we have a filtration. And this one carries an action of the Galois group. And then there's a filtration. And this isomorphism is not just sort of a naive isomorphism. It's an equivalent for the Galois group action in such that somehow the Galois action on the left, I can diagonal on this one, whereas Galois action on the right only acts on the left bit here. And the filtration is also compatible. And also, you can say that, so how do I recover this HI? Durand, x over k, as we did above. Well, remember how we did was we start with the Betty cohomology. And then I just basically need to kill the last part by taking, I guess, invert under the Galois, that gives me complex conjugation. Now I can do the same thing. I can sort of take this étale cohomology, and then I tensor with the speed around. So why this comparison theorem? I get to the right hand side. Now you see that this one doesn't have the Galois action. So therefore, I can take the Galois action and somehow kill some part of this. It turns out that the Galois invariance of the speed around is precisely k. Once you take the Galois invariance, you just recover the speed around. So this is, in fact, while this isomorphism, this is isomorphic to hi. Tensor with V around over Q. And together we take Galois invariance. In fact, moreover, because of the filtration compatible on both sides, this entanglement doesn't have a filtration. Or rather, you can think of it as a filter space where everything is constant in the degree 0. But the speed drum carries a filtration. Once you take the Galois invariance, it still has a filtration that agrees with the hot filtration I defined earlier. So this is a periodic hot theory. This is a standard periodic hot theory. Not that sort of situation. So let me make a remark that maybe right over here. So Fontaine constructed the drum, and comparison theorem was proved. It's proved by Faltings first using and Trudy. I think these two proofs almost come out around the same time, and it shows they give a simpler proof later. Okay. So for our purpose, this is great. I'll review the definition of speed drum later. For our purpose, we need a sort of integral version of this, or rather a sort of slightly easier version of this. And also we'll talk about a case where these two somehow combine together. Let me make our life a little bit better, even better. So right now, this case is just arbitrary completely square radial field of capital 0 with perfect radial field. So now let's assume further that K is absolutely unramified. Nice. I.e., E is a uniform either. For example, I know a field that's absolutely unramified. Okay. And I'm going to assume that X has a good reduction. I can find an X proper smooth over OK such that Xk is isomorphic to X. Okay? So the picture I'm looking at is a spec OK. The X. And I have this sort of generic fiber. That's my X. In the sense that I guess maybe I should start from the X here. I have a way to extend it still in a proper and smooth way. To a proper smooth variety over OK. And then I can sort of talk about the special fiber of this. Okay, next step. Now I want to sort of write down a similar comparison like this one. Maybe write this one to the star Duran, because it's Duran and Etal comparison. I'll give a different comparison right away. So this is similar. On the left hand side, I start with H tau I. going to introduce something called crystalline cohomology. You don't have to know what this crystalline cohomology is. I'll say what it would look like in a minute. So once again, I want to compare these two. Maybe before that, let me say what this crystalline cohomology is. So before doing that, maybe I should write xk. Classical notation is sk over ok. What is this thing? The definition of this is a bit complicated, but there's an easier way to think of it. Especially in the case when you can lift your x, especially when you have a form of smooth model over ok. This cohomology is very easy to compute. In fact, somehow this hi of crystalline cohomology of xk, okay, is the same thing as the de Rham cohomology, or at least, at least tensor with k after inverting p. I'm over here. I'm going to invert p anyway, so this is isomorphic to the de Rham cohomology. So we can say, I guess one way to think of this is that you can say that, okay, it's just another way to write the de Rham cohomology and give it an integral model. That's true. But there's additional thing you can harness from this, or maybe there are three things. One more thing is that this crystalline cohomology has a property that the reason I wrote this is because see, it doesn't have anything on the generic fiber. So this depends intrinsically only on the special fiber. It does not depend on the lift. But whenever you have the lift, it will be isomorphic to the de Rham after inverted p. It will be isomorphic to the de Rham cohomology. But by itself, how it's defined, it only depends on the special fiber. The way it's defined is that you basically one basic pick is set locally at least some sort of arbitrary lifts, and then compute the de Rham cohomology in the generic fiber, and show that somehow such defined thing does not depend on the lift. One more thing. Because it depends only on intrinsic on the special fiber, this crystalline cohomology carries the action of Frobenius. Absolute Frobenius. I mean, when I say Frobenius, I mean absolute Frobenius. So that, I guess usually we take the absolute Frobenius. So the absolute Frobenius will change. I mean, absolute doesn't act on capital X, but will act on a special fiber. So or I guess it does, but somehow. Anyways, this crystalline cohomology will act out here, and therefore, I'm going to call this phi action. So what we have here, we'll have an additional phi action here. Right. So now I have to sort of complete the picture. Over here, I only have the Galois cohomology as well. In this situation, there's some other ring we can use, which is smaller than speed de Rham. We can use to put in here. This is called B Cris. And this ring carries the Galois action, a phi, and a filtration, which will inherit from the B de Rham. And also, we will not talk about filtration here. In fact, we will have a filtration inherited from B de Rham, but for this comparison, it only states that you have a Galois group and a phi here. Oh, phi is safe. So this is star crystalline comparison. for for our later purpose, so this is great. So in fact, one can sort of combine this. Let me see. Let me put it over here. So, okay. So we will have this, but then I can combine. Oh, maybe here's the fact. As we'll see in the construction, that B Chris is a subring of B dot. So I can combine this and the other comparison, and be like, so now I have my H, and also the isomorphism of this crystalline convex compared with surround. So I can put this together. So I can combine the two comparisons in the following sense. So let me just write it as so. We actually invert P. Over here, I could. So this is a QP. This is a QP algebra. So I can either do that or I can invert P and then tensor over K. That's going to give the same thing. So let me invert that and then tensor with K. So I can compare, I can combine these two comparisons. So first of all, this comparison here, I have Galois action here. And this one carries a Galois action of a phi action on this B Chris. But also, I have something that inherited from B Durham, because B Chris is a subring of B Durham, so this filtration will restrict to a filtration over here. So I have a filtration from the Durham side. Similarly here, I have a phi action. And via this isomorphism with the Durham cohomology, this one naturally inherits a filtration coming from the Durham cohomology. And similarly, this one has a phi. And the whole thing is, so all these sort of the yellow and red symbols, they're all compatible in the sense that Galois acts diagonally here, the phi here acts diagonally, and filtration will be somehow the combination of the two filtrations through in a natural way. Right. So I want to say that just like what we have over here, we can, if we take Galois invariance, then I will basically kill this term here. Just like how I kill, let me add another fact here. Oh, I didn't write this B Durham invariance here, sorry. Here's the fact. I'll rewrite these facts later. Invariance of the Galois group is the same thing as B Chris under the Galois group. Okay. All of these are under assumption that K is absolutely unramified. So therefore, if I take Galois invariance, B Chris taking invariance on the Galois group is still K. And therefore I deduce that somehow Hi of Chris of xk can be expressed by starting from the Italian cohomology. On the other hand, I can recover the Italian cohomology from the from the crystalline cohomology as follows, by somehow taking, I guess, just look at which action doesn't have here, by killing the phi action, and then taking the field 0. But here's another fact about it. So if you take phi Chris, and take phi equals 0, excuse me, phi equals 1, and then take the field 0 part of this. This is again. This is another sort of fundamental fact about this. So that means that if we take phi invariance and field 0, what's going to happen? That the right hand side you will get whatever I get. On the left hand side, if I take the phi invariance, this étale common doesn't get hit. Only the phi invariance not taking on this part, and then filtration. So therefore, I get hi. I just recover. Oh, excuse me. My bad. This is invariance and this is equal to qp. My bad. So if I take phi equals 1 and then field 0, this will just become qp. So this is tensor over qp. So therefore, it's the same thing as without tensoring anything. So étale common of this one will be isomorphic to the crystalline cohomology of xk over ok. 1 over p tensor with over k with b Chris. With phi equals 1, and let me just write field 0 here. I'm taking the field 0 as this part. Maybe let me also mention that, I guess in the first case, I'm taking the Galois invariance, but there are intrinsically things happening here. So this one over here, you have a phi here, and this one doesn't have a phi, and this one has a filtration here. This one doesn't have a filtration. But somehow when you're taking variance, this phi action, the filtration still sort of stays in here because they all commute, and they are precisely the phi and filtration we have on here. And conversely, if my so over here I have a Galois. This one doesn't have a Galois action, but over here I have a Galois action. After I kill off the phi and filtration, I'm left with a Galois action. And somehow, in some sense, in this very nice situation when k is absolutely ironified, and x having a good reduction has a good reduction, in such a situation, H Durham cohomology and this crystalline cohomology, if we insert information of the comparison with Durham cohomology, altogether, they kind of determine each other. So that's the upshot here. Upshot. In this case, étale cohomology and Durham and this crystalline cohomology. Plus Durham, maybe I should say. Determine each other. So, right. So let me. I think we spent too much time without giving concrete definitions. Let me do that here. Let me give some concrete definitions. Talk about these rings. The second part. Definition of PI theory rings. So I start with a K, a complete discrete Lagrange field with residue field small k, perfect of characteristic 0. And I want my k to be characteristic 0. So that's the setup. So from this k, I can define, now people don't write the CP here. According to Schotel, he just writes C. I still like the element which has CP. This is defined to be the algebraic closure of this K. And then take sort of PID completion. So right now my K does not have to be absolutely unramified. We'll talk about that later and see where that comes in. And then write OCP for the ring of integers. So now this shows us tuning definition. I mean, of course, this exists. This was introduced by Fontaine. So this is really introduced by Fontaine, but it shows that it's made it, I guess, more conceptual. So this is not B. This is flat. It shows it writes the musical. This symbol. It's flat. Wait. Right. This is a flat. Right. It's defined to be the inverse limit of OCP modulo P times OCP. Note that the P is not a uniformizer of OCP. So inside this equation, there are a lot of terms like P to the 1 over n, for example, n to the P. They all kind of belong here, which is not 0. So this is a very, very non-reduced rate. What do I mean by this inverse limit? I'm really taking a sequence. I'm taking a sequence as so, where each xi is now an OCP modulo P. And such that they're compatible, so inverse limits are a compatible sequence, right? You want xi to the pth power is the one before that. So maybe let me give you an example of an element here. So the example will be 1 zeta p. So basically, this inverse limit is that you start with 1, start with the element, start to take pth roots of that. So zeta p, and zeta p squared, and zeta p cubed, and so on. This is a particular element here. So let me write here that if the n is a primitive p to the n roots of unity, and I assume that the n is zeta p. That's basically what this says. This is a particular element here. I'm going to call it epsilon. This is of great importance for PI plot theory. Let's fix such thing. So remember that if I take a ring and then quotient out by an ideal generated P, that's still a ring. And even if I take an inverse limit, but note that raising to p's power, I mean this ring is in characteristic P, although it's not reduced, right? I mean, P is 0 in this ring. So therefore, in characteristic P, raising to p's power is a homomorphism. So this inverse limit is a ring. So this is has a ring structure. This is given by term-wise addition and multiplication. Because raising to p's power is a homomorphism, so therefore the approach is positive. And I want to say this is perfect. It's a perfect ring after you take limit. That's because whenever you get x0, x1, and so on and so forth, this is the p power of x1, x2. Basically shift index, because the x1 to the p power precisely x0, and x2 to the p power is precisely x1, and so on. And this one also carries a valuation. This valuation gives us hold on. Let me write VP flat here. This is on x0, x1. So this is equal to p to the m. I evaluate take the p evaluation of the mth term, and then multiply that with p to the m. The reason is that I want to pick m such that xm does not belong to p times OCT. What is going on? So here's what's going on. example, and you'll see why I define things as so. So give an example of why I'm doing this. Let's see. So say I have this epsilon here, right? Let's compute epsilon minus 1. Okay, everyone knows how to compute epsilon minus 1. So this is 0, right? 1 minus 1 is 0. And then zeta p minus 1. Zeta p squared minus 1. Right? So if I want to compute the BP flat of epsilon minus 1, you see, okay, I can't use this pi divided from 0. It's 0. Okay. Sorry, excuse me, it's infinity. But then we know this is not, this epsilon minus 1 is not 0. Because the next term, I guess the point is that supposedly this term should be, this 0, by extension it should be zeta p minus 1 to the pth power. But when you but we know that this one has valuation 1 over p minus 1. If you raise to pth power, it's valuation strictly bigger than 1. But I'm quoting out anything that's divided by p. So therefore this becomes 0. So you can't really see the evaluation here. So instead, I have to define it to be p times the p-adic evaluation of something we can see, namely this thing here. So I get the valuation given by p over p minus 1. Okay? You could use the third term. This is also equal to p squared times p-adic evaluation of this term minus zeta p squared minus 1. But this will give the same answer because modulo p, this to the pth power is precisely this one. Okay? That means modulo is sort of a higher small terms, error terms. These two are sort of same thing. Therefore they must have the same valuation. And because of that, if you add margin up, this definitely will make sense and then will not depend on this add as long as argument. So I can define the valuation of this ring. So this inverse limit is a perfect valuation ring. And maybe I show you this in characteristic P. So I'm taking inverse limit to a characteristic P field, so it must be also of characteristic P. There's no doubt. Okay. So now, for our later application, I'm going to give a equivalent way to write this, which looks very much different. So it turns out that I can also take the inverse limit of OCP without quotient out by P. That will give me the same set, or rather same abelian group, but no explicit ring structure. Okay? So I can take inverse limit of this, but then this just as a set, it looks like so. It doesn't have a ring structure in it. So how does this two correspond? Let's see. So let me say I have a x0 written as x0, x1, and so using lowercase indices. And I'm mapping it to this inverse limit. I'm going to write uppercase, so x0, x1, x2. This inverse limit. And I want to define, let's define these. So the way I define this is that xn is, I can take the limit of m going to infinity of taking xn plus m. Now some number way after this xn. And then and I lift it arbitrarily to an element in OCP. And then I raise to p to the m power. And this will very close. It's really close up. And as m goes to infinity, you can check that this take arbitrary lifts, and this will kind of converge to some number. So this is long OC. It's very clear to see that. I can see that, so these xi's are compatible by raising to p power. Okay. So this is OC. So this is a tilting process. think let me introduce CP flat. This is also, we see that what we have here is a this is also complete. One more thing, complete. It's relatively easy to see because I guess OCP is complete and somehow we take limits somehow. Things nice. Things works nice. Right, what am I doing? So we get that this is a complete valuation field, which is perfect in characteristic P. But this is integral because I started with OCP. So all the valuations are greater than or equal to 0. So now I just have to invert something with negative with positive valuation. Namely, for example, let's choose that 1, epsilon minus 1. It has a positive valuation. I invert that. So now I get a field. So the CP flat is called the tilt of CP. It shows this philosophy that whenever you have a deeply ramified field in characteristic 0, the mixed characteristic field, you could use this process and get a complete, a complete perfect field in characteristic P, which is called tilt of that. So I'm going to leave this board here, and I'll define this important on this board very quickly. So, right. So now I'm going to define so-called A in. This is a weight vector of OCP flat. So we've learned weight vectors for a perfect ring. This is for a perfect field, actually. But in fact, the weight vector works for a perfect ring as well. So this is a perfect ring. So I take a weight vector of that. This is called an A in. So this is a very important, I guess, ring in the PI Hawk theory. I remember a joke. So Comas wrote I think probably a memoir of Fontaine, and he said Fontaine introduced this ring A in. It's a ring that controls all other rings. So every ring comes from this A in. It's the Lord of rings. So there's a natural homomorphism. There's a natural homomorphism from theta from A in, which, let me write it again, going to CP. In fact, this goes to OCP because I'm taking an integral version of this. Later on, I'm going to use a sort of a non-integral version. I'm taking a weight vector of the CP flat going to CP flat. At this moment, I'm just having this. So everything in the weight vector, I can write it as sum of Pn times a Teichner lift of its corresponding element for n greater than or equal to 0. And I'm going to set that to, well, this is a ring homomorphism, right? I got to have the sort of Pn, same thing as here. But this An, I'm going to send it to An circ 0. What I mean by this is that I have this An, which is in the OCP flat. So I want to take this realization of this An. When I take this realization of the An, I will have sort of An. This is my An. So this An will be represented by inverse system, and then taking the first one. And this is a homomorphism. And here's another fact. That the kernel of theta is the Teichner lift of this epsilon. Where's the epsilon? The epsilon over there, minus 1. Well, why is that? For this epsilon, it has a very good thing that in some sense, you can write, so this 1 zeta p squared, so forth, you can write it in the the mod P version, you have that. But if you turn that into this this integral inverse limit, you can still use the same representative because you see that zeta p to the I, p power is still zeta p to the I minus 1. So it still satisfies the inverse system sort of condition. So therefore, this is the same thing. So now, what is the image of under theta? So this is because, so note. Let's check one way. So theta of epsilon, theta of 1 is definitely 1. So theta of epsilon is precisely the first element in that. So namely just 1. So therefore, theta of epsilon minus 1 will be 0. So at least this element is in the kernel of this theta. As it turns out that this is the generator of the kernel of theta. This is not a trivial fact. But I want to say that I guess our goal is not to sort of give a full lecture on Hawk theory. So our goal is to sort of, I guess, by putting somehow for to see at least for once that how things are put into these places. And for our applications later on, we'll only use very tiny bits of this. Or I can take this as a black box. So once these are done, I can introduce the period rings, the B crease and B drops we used earlier. Before that, I need an integral version of that. So let me call it A crease. Maybe I'll just define B crease drop first. You know what? Let me do A crease. So what's happening here is that inside this A inf, now I have an ideal, which is kernel of theta. So I didn't have time to talk about there's no way I can talk about the crystalline cohomology. The crystalline cohomology is a very important thing for divided power construction. So whenever you have an idea of the ring, you want to sort of talk about, in sentence, we will talk about Taylor expansions. But Taylor expansion has a downside, namely as n factorial in the denominator. So the idea is that somehow we want 3 n factorials in this ring, in some sense. So this is the following construction. So this is the divided power envelope of kernel theta in A. Namely, this is all the following things. So I want to be able to take n factorials, but the coefficients. I allow things as follows. So I allow things as a sort of power series expansion, or sort of Taylor series expansions, where this x here, I can take it to be anything in the ideal kernel theta. But of course, my kernel is principal. So what ends up happening is that I'm taking all such power series where this is sort of epsilon minus 1 to the n power over n factorial. Over here, I have n here for n equals to a n. And then I take a completion. Maybe I should say completely divided power. Okay. So I guess it's just sort of finite sum and then take completion. So that somehow it's an infinite sum, and then the an will go to 0. Okay. So that's what it looks like. It's a bit complicated. Nonetheless, this carries a forbiddance action. And this one carries a Galois action as well. Okay, so the forbidden action comes from here. So on A inf, it's a weight vector of a perfect ring. So any weight vector has a forbidden structure. And so it turns out that of course, the forbidden action will act here as well as here. Phi acts on this expression will get to another sort of sum of such expression. That's for sure. But you can show that I guess you can show that whenever you have such things, if you feed sum therefore it's stable under phi in some sense. And Galois action is sort of the same thing, because my Galois group acts on OCP, and therefore acts on a weight vector of such things, and then acts over here. So P-Durand is similar, but simpler, really. This is the completion of. Oh, maybe I should say n a n goes to 0. So I don't have to write this completion for anything. So P-Durand plus. So in pure Hall theory, whenever I write A, there's a important thing which is integral. So P integral. In the sense that although I have denominator a n factorial here, all my ANs are in weight vectors. So there's an integral structure here. But whenever I write B, always mean P inverted. This is sort of the standard. Okay, so when I write B Durand plus, so therefore B must be inverted here. B Durand plus is a completion of weight vector of this CP flat. Over here, A if it's OCP flat. Here I have CP flat. This is rather similar. That's why you get very different rings. And kernel of theta going from the weight vector of CP. So it's the same map, theta. Except over here I take the sort of the CP flag. Namely, I have somehow negative evaluations allowed in here. And this can be also mapped to CP. And this is subjective. And also, I forgot to say earlier, this is also subjective. Basically, start from any AN cert. You can find an AN. So this is completion of this adds this. In other words, you can rewrite this as sum of all these things. AN. Of epsilon minus thing. Where AN is the weight vector. So this is a characteristic of 0. Okay. And this one carries again a Galois. And I want to say that this is a discrete valuation. Turns out this is discrete. You're taking this here brain, and there's a function here, and then you look at the how should I put this? You can, I guess, maybe put it this way. So essentially, because the kernel of the theta over here is epsilon minus 1, this kernel is also generated by epsilon minus 1. So therefore you have a ring which maps to a quotient which is a field. And the kernel, that means this kernel is the maximum ideal of this ring here. And also the maximum ideal is principal. So that basically the completion at this maximum ideal is, well, if the ring is not crazy, then it's, or a nice ring, then its completion must be a complete discrete vector. This is a complete discrete valuation of the ring. It's uniform either. Because at the moment epsilon minus 1 and the rest of the field CP. The valuation of maybe B Durand plus straight B Durand of this is precisely 1. Or rather, any term as so. Any term as so, just see how many and how valuation of B Durand. valuation is. And this one carries a filtration is basically by just counting the valuation. This is all the elements x in beta-rom. The beta-rom valuation of x is greater than equal to this is a decreasing filtration. If I gets bigger, you require more conditions on the valuation. Then the space is smaller. And beta-rom is a fraction field of this. It's completely square-Western ring, so the fraction field is inverting any element, any three uniform item. Okay. That's it. But here's some sort of a kind of another thing. Another complaint is that this element epsilon minus 1 is not very nice in terms of Galois. So we want to use a different element which works a little bit better. But at least I defined what beta-rom is. It's a completion of this weight vector of this CP flat at some sort of quotient ideal. Maybe I can just say morally. Somehow this beta-rom I'll also that later. But after I introduce it here. So I need another variable, a different uniformizer, which works a little better. So right, t to be log of epsilon. So I'm going to change epsilon a little bit. This is not working very nice under Galois action. So let's do log. So by definition, just taking Taylor expansion of this. So it's taking Taylor expansion of this one. Let's see. In fact, this also belongs to a increase. Because I'm taking some sort of Taylor expansion in epsilon minus 1. And the a increase allows me to have n factorial in the denominator. I only have n in the denominator, so that's good enough. So this belongs to a increase plus. Of course, by how things are defined, basically, beta-rom plus has no condition. Know that my a can have denominator. An for when I define beta-rom plus, an can have denominator. When I define a increase plus, an cannot have denominators. So therefore, I guess even if I have n factorial in the definition of a increase plus, that n factorial in the denominator can be combined with an to define beta-rom plus. So this is the sum. So it's a particular element in a increase plus and also in beta-rom plus. And you see that also in terms of uniformizers, right? This has valuation 1, and this has higher valuations. So T is a uniformizer of beta-rom plus. So this is a preferred uniformizer. Let me make a claim that T is a periodic 2 pi I. What does that mean? Well, think about what's 2 pi. So E2 pi I is 1, right? So you're taking, I guess, log of 1 to get 2 pi I. So this epsilon looks like sort of periodic of 1. Sort of 1 epsilon zeta p squared. Somehow, I don't know how to say it. When you take log of this, it looks like somehow taking log of on the real world, taking log of 1. Okay. And what's more important for this one is that I want to claim that why do we like this particular T here? That's because the Galois group GT is equal to cyclotomic. So Galois group acting on this element T via cyclotomic character. That's because of following for G in the Galois group of. That's because see how the Galois group acts on zeta p to the n.
rather this is how cyclotomics are defined. Cyclotomic characters are defined. It's raising to this cyclotomics of g's power, right? So if I do g of this epsilon, let's first of all do it without the Teichmann limit. This is just epsilon to the cyclotomic character, to the g's power, right? Because each of the entries, so this epsilon is the collection of this p to the n zeros of unity. You're just raising that to the cyclotomic g power. And now I take Teichmann limit of this. Right? And then this is the same, right. And then because Teichmann limit is multiplicative. So I take this out. Now I take log. If I take log, this becomes multiplication of that. So that gives me. In other words, t. In other words, here's another way to write what we just did. If I do QPT, this is just QP1. Because the action on t is just given by cyclotomic character. T is an eigenvector. Okay. And also, for a similar reason, what about the Frobenius phi t? Again, if I have a cyclotomic, if I have root of unity, I just raise into p to the power phi. Or phi comes from here, my bad. So phi of epsilon. By how Frobenius defined for weight vectors, this is just Teichmann of p to the power. Just to the p to the power. And then take log. You get pt. So there's another formula we're going to use there. Okay, we have these things. So now, let's see. With this at hand, let me write it on the other board. I don't need this AA anymore. Let me say a little bit more about this B Doral to give you some sense of what this sort of crazy ring looks like. The crazy ring doesn't look like that crazy, but anyways. But somehow well, we'll see. So let's see. So what is phi I? Now I can write this a little bit better. So what is phi I of B Doral? Phi I of B Doral will be, or plot. I don't need the plot here. I can do it for any I. So phi I of B Doral is taking elements in this B Doral. Oh, I see. I guess let's swap these two. Define B Doral as so, and then define filter B Doral. Filtration of B Doral as so. Right. So what is phi I of B Doral is those elements with valuation running to the I. So I can rewrite this as t to the I times B Doral. Just like in any complete discrete valuation field, right? Those elements with valuation I could be written as uniform magnitude i's power times ring of integers, so B Doral plus, right? And therefore, what is the graded piece of I of B Doral? So this is Ti of B Doral plus modulo Ti plus 1 B Doral plus. So essentially Ti times B Doral plus modulo T B Doral plus. Right? But what's the TT is uniformizer? Or rather, somehow it generates it doesn't quite generate that kernel, but somehow the quotient by this thing by the I guess this quotient B Doral plus by is this T times this maximal ideal. You get the residue, which is CP. So this is TI CP. In terms of Galois module, this is CPI. So B Doral is the extension of CPIs for different I. But this is a non-trivial extension. So in other words, So I deliberately write this is not the same thing as direct sum of Cp to the I. As Galois modules is not let me think. I'm not so sure. Definitely not as. So B drum is different from this one. Definitely not. They're not the same thing as topological Galois modules. I forgot what happens for the non-topological version. But somehow morally looks very much like that. So that's in the sort of comparison theorems. That's what the B drum looks like. Whereas B Chris is a bit complicated. Why B Chris is not. First, I define B Chris plus. This is A Chris plus inversion P. And then B Chris is equal to B Chris plus inversion T. Great. So here are several facts in general. So B drum plus, if you take the Galois invariance, or rather same thing as B drum taking Galois invariance, that's equal to K. And the A Chris plus, if I take Galois invariance, that's the weight vector of K. And the B Chris Galois invariance is equal to, or I should say, A Chris plus Galois invariance, it's equal to, it doesn't equal to K in general. So earlier we talked about that's equal to OK. That's because this K is absolutely unramified. In general, you only see the weight vector of the residue field. Same for B Chris. So this is the weight. This is the, I guess, this is the maximal unramified. So the maximal absolute unramified subfield of K in general. And also, most important thing we discussed before, this one, if I intersect with the field 0 B Chris,